All right. So the following, let's say, would I still name those? Okay, so if you have two linear maps, like from B to Q first, and then U to W, because this is the linear map A head, and this is the linear map B head. The composition, so you first go with A and then B. This is a map from B to W. But we showed that actually it's a linear, okay? Since it is linear, we may talk about its matrix representation, right? And the fact is this, so let me write as a proposition. Beta 1, beta 2, and beta 3, the basis for the U and W respectively. We assume that all the vector spaces are finite dimensional. Scaling. Excluding all vector spaces. Are finite dimensional. Okay. Here we don't have to assume that. I mean, this vector space can be in a dimension, but for the statement of this proposition, I need that because I'll talk about matrix dimensions. Then the conclusion is this. Then for the matrix representations of A heads, E heads, and we have composition A head, we have what? We have the following. The matrix representation of this composition. From which basis? Now, here I have the basis. All right, let me say. So here I have the basis beta 1. Here I have the basis beta 2, and here I have the basis beta 3 for these vector spaces. So this composition is a linear from B to W. So I may talk about the matrix representation from this basis to this basis. So from beta 1 is beta 3 is what? This is the composition of DNA. So here I have we have, and then here I have just matrix multiplication, and the bases are like this. First, I go from beta 1 to beta 2 via A, right? A is from B to Q. So here I have the basis beta 1, here I have the basis beta 2. So I have the matrix representation of A from the basis beta 1 to beta 2. And here we have B, which is from beta 2 to beta 3. So that's the formula, okay? You may keep in this in mind as follows. This is like if you just cancel these. And then data decomposition A, which makes transition from data 1 to data 2. These are kind of transfer. Okay? And the proof is, simple. So let's see. We have seen already that this is a linear map, right? So let's denote it with C. And suppose I have this basis. So data 1, let's say it has n dimension. Data 2 has, let's say, n dimension. And data 3 has, let's say, k dimension. So let's say, okay, H1 up to H2. Okay. Well, now, what are the entries of A? Recall it. A and J are the following. So you write AI, right? And this is a sum of things like this. Here I have J, and here bunları ben kolum olarak yazacağım, değil mi? Kolum olarak yazacaksam JI'di değil mi? C nereden C'ye? Birden N'e kadar. Burada elde ettiğim şeyleri bu i'inci. So this is the ith column of the matrix A. I is fixed, J is changing, right? First column, second column, third column, and so on. No. We are in the jth column, first row, second row, third row, and so on. Okay. What about B? Efendim? Bunlar i'inci sütun olacak. Sütun. Tamam. Yok, i sabit, i'inci kalın bu. İ'inci kalın. Roller değişiyor. Tamam mı? Birinci vektörün katsayıları birinci kalımı. İkinci vektörün katsayıları ikinci kalımı veriyor. Aynı şey burada geçerli. F let's say I demeyelim değil mi buna? J diyelim. J desek B K'yı kullandık. L J F L L from 1 to K. Tamam. F yok. M olacak. F'i kullanmayacağım. Burada H kullanacağım. H K. Tamam. Değil mi? Evet. Burada yok. F'in imajı H'ler cinsinden. Değil mi? This is the basis for the second vector space. This is the basis for the third vector space. So here this. Okay. So C head AI. C head AI is what? This is just B head composition A head of EI. This is just B head of E head of EI. This is B head of A head of EI is what? It is just this digit. J from 1 to M, A, J, I, F, J. Since this is a linear map, it respects linear combination, so that I can take this sum outside and this scalars outside and write this. A, J, I, B, head, F, J. Okay, so I just took the sum outside and this constants outside because B is a linear map. I have this. Now for this one, I have this formula. So we have C head of EI is equal to J from 1 to M, A, J, I, and then B of Fj. B of Fj is just this expression. So L from 1 to 2, E, L, J, H, L. And again, I can just take this summation outside or take this scalar inside. You may think it both ways. So we get summation over J and summation over L, A, J, I, B, L, J, H, L. But let me also write it this way. Ya da şurada yapayım. Şimdi bu ikisinin yerini değiştireceğim. L from 1 to K. And then write this as follows. From 1 to M. And D, L, J, A, J, I, H, L. Şimdi bunun ne olması gerekiyordu? This is the linear map, and I write the image of the ith basis element of the domain as a combination of basis elements of the range. These coefficients, then are what? These are the coefficients of C. What was it? C'nin olması lazım. C. C'nin L'inci kalın olacak. Yok. I'inci kalın olacak. L, I. Evet. Tamam. Demek ki C, L, I bu olmalıymış. Right? These coefficients, whatever they are just the coefficients of the matrix of the transformation C. So the conclusion is that this matrix representation, so the matrix representation of C has coefficients this, and this is nothing but J from 1 to M, D, L, J, A, J, I. So this means what? This matrix is nothing but the product of the matrices B and A. And hence C is just B times A. C dediğimiz yani kompozisyonun matrisi gösterir. C head is this. This is C head. Matrix representation of C head is just matrix representation of B times the matrix representation of A. Tamam mı? İkisini çarpıyoruz. Sorusu olan var mı? It is confusing, but they are not, you know, difficult. I mean, it doesn't have deep ideas, you know, complicated ideas. We just use definitions, right? Each time you have to remember what is the matrix representation, what was the basis, and so on. If you just keep them in mind, and if you do enough exercises by yourself, then you just get used to it. Okay. We can do an application like this. Let me change the board. Suppose a head is a linear map from B to B. Okay, and B is finite dimensional. Let's say, and beta 1 and beta 2 are two bases for the same vector space for B. Then we may consider the following. Let's say we consider the following map. B is just identity map, composition A, composition identity. So where is the identity? Right, if you compose something with identity, of course, you just get this, and then you compose from this side also with identity, you get again A, right? So we have this. First, I go with identity, and then with A, and then again identity. Composition is, of course, again, just A. But writing this way is the following consequence. I can do the following. So I said this is, but actually we just saw that this is just A hat, right? It's not a new thing, it's just A. Now I can do this. The matrix representation of A from B2 to B2, from the second basis to the second basis, can be written like this. I will start from beta 2 to beta 1, beta 1 to beta 1, beta 1 to beta 2. Okay. Right. I am just applying what we have seen over there. Identity mapping bu bazdan bu baza matris gösterir. Bu identity matrisi olmayacak. Right. Now, let P be the following matrix. Okay. Then, of course, we have the following. Then, you see, identity from beta 1 to beta 1, beta 2 to beta 2, can be written like this. Identity times identity. Here I have beta 2 to beta 1 and beta 1 to beta 2. I can write this. What is this? What is this? Identity map from a basis to itself. So if I put here I of EI, then what is this? This is the identity, so EI. And EI written in this basis as what? Well, 0 times E1, 0 times E2, up to 1 times EI, and then 0 times EN. So, what is the ith component of this? It is 1, all others are 0. So, this matrix is nothing but the identity matrix. This is not identity, because you write, in this case, EI in terms of FJs and the coefficients, will vary. But if you write identity from a basis to itself, then you have this. Therefore, the ith column is what? Ith column, it is like this, 0, 0, 0. Ith row is just 1 and then 0. So this is like this: 0, first column, second column, third column, and nth column. What is this matrix? It's just the identity matrix. So this is just identity, but that means what? Pardon? Yeah, well, sure, we are using associated. Okay. So what we see is the following. Then, hence we have the identity matrix, and by an identity matrix is what? Is this matrix times this matrix, beta 1 to beta 2, beta 2 to beta 1. Değil mi? Ve şurada identity çıktı. Hangisine P demiştik? P, şuna P demiştik. Beta 2'den beta 1'e. So I just call this matrix P. Like this is the matrix P. P times this guy is equal to identity. This means what? This has to be inverse of P, right? Thus, beta 1 to beta 2 is just inverse. Okay. Yok, tahtayı değiştirmişim. Okay. So, this is identity, and we call this matrix P. Therefore, this has to be P inverse. So, what we see is then, if I come back here, what we see is then is the following. This is the matrix P. I'm sorry. This is the matrix P inverse. Okay. So all right. So this is the matrix P, and this is the matrix P inverse. So we get the following. The matrix representation of A hat in a basis, let's say beta 2, is equal to what? Is equal to P inverse here. The matrix representation from beta 1 to beta 1, and then I have P here. Okay? Where is the following. This is the matrix representation of the identity map from beta 2 to beta 1. Okay. This is a very useful formula which we will make use of a lot. And actually, it's a simple consequence of several little things. Definition. Okay, bir tane örnek bakalım. Okay, let's the following. Bu Fibonacci sequence için bir matris bulmuştuk. Neydi o? 0, 50 olsun. Yani daha doğrusu şöyle. A is considered as a linear map from R2 to R2. This 2 equals 1, 2 equals 1, given by a head. Okay. X1, X2 is just X2 here, X1 plus X2 here. Right? And in the basis, now if beta 1 is this basis 1, 0, 0, 1, then of course, then what is any check of 1, 0? So what does this to a basis, to a vector? It takes this element up here and take the summary right here. And what is this? This is just E2 and so. So this is E2, where the 0 times E1 plus 1 times E2. What about a head of 0, 1? So this is E1, this is E2. Okay, this is just 1, 1. And what is this? This is just 1 times E1 plus 1 times E2. Hence, the matrix representation of A in the basis beta 1 to beta 1 is what? First column is just 0, 1, and second column is 1, 1. So, just the matrix representation of this feature. Okay. Şeylerle, eigenvektörlerle ilgili biraz işler yapmıştım değil mi? Bu EYT'in eigenvektörlerini bulmaya çalışalım. Let's try to find eigen values, eigen vectors of eta. What was the definition of eigenvector? Eigenvector is a vector which is not 0. So this will be a vector in our vector space, which is 2 by 1 matrices. So that A times B should be lambda times V for some for some lambda. Lambda can be 0, but V cannot be 0 by definition. Eigenvector is this. And we have seen the following. This implies what? A times lambda times identity times V is 0, right? Because V is just identity times V. Yani şöyle biraz daha uzayabilir mi? AB minus lambda B equals 0. But lambda B can be written like this. Identity times B equals 0, and this is just this matrix times B is 0. And since this vector is not 0, this matrix right? So we are trying to find the eigenvectors and eigenvalues of a head. We write the definition for eigenvalue and eigenvector, and we obtain this at the end. This is a linear operator applied to this vector, and it is 0. If this were invertible, then multiplying both sides with its inverse, we would get V equals 0 times a vector, or a operator times 0 vector. That would be just 0. So we would get V equals 0. Okay? If A minus lambda I is invertible, then just applying its inverse, A minus lambda I inverse A minus lambda I, V is A minus lambda I inverse times the 0 vector. This is 0, and this is just identity times V. Well, we will get 0, a contradiction. So this implies what? This cannot be invertible. But if it is not invertible, okay, so A minus lambda I is not invertible. What is this? A minus lambda I. A is just this matrix 0, 1, 0, no, 1, 1. Lambda times identity is just this, right? Identity times lambda is this matrix. So what is this? This is just minus lambda, 1, 1, 1 minus lambda. And since it is not invertible, this determinant of this should be 0. So we should have this. But what is the determinant? Determinant is just product of these two minus product of these two. So it is minus lambda times 1 minus lambda minus 1. This is just lambda squared minus lambda plus minus 1. Evet. So this should be 0. So we obtain an equation for the eigenvalues of this operator, right? This polynomial must be 0. Well, you know how to solve this, right? Even ancient Greeks knew that. So it is just 1 plus minus 1 plus 4 divided by 2. So we get 2 eigenvalues. We get 2 eigenvalues. What are they? So number 1 plus root 5 over 2, and number 2, 1 minus root 5 over 2 are the eigenvalues of the matrix A, which is just 0, 1, 1, 1. Do you know these numbers? This number is lucky, it has two names, right? One of them is 1 plus root 5 over 2. The other one is golden ratio, right? I am saying they are lucky because, you know, almost no number has a name. Why is that? Because the number of names is countable. You can count the names, right? We have dictionaries, and they have finite number of you know, strings of letters. Even if you consider infinite, no, that's not true. Any name should be a finite number of strings, and therefore they are countable. But the number of real numbers is uncountable. It means not all numbers can have a name, only the lucky ones, and the percentage actually 0. But you know, we have so many of them. Yani bir şeyin ihtimalinin 0 olması o hiç olmayacak anlamına gelmiyor, değil mi? İşte dediğim gibi. Size bir sayı söyleyin desem ne diyorsunuz? Ya rasyonel sayı söylersiniz ya tam sayı söylersiniz. Onun bütün sayılar içindeki oranı %0. Ama herkes gidip o %0'dan bir şey söylüyor. Okay. So these are the eigenvalues of this matrix. What about eigenvectors?
Could you give the definitions of eigenvalue and eigenvector?
I gave last time. Random. Buna eigenvalue, buna eigenvektör denir, değil mi? Okay. So let's definition. Let's inherit from definition be an operator. So from a vector space to itself, okay? Or a field K. This is a vector space over the field K. A vector be in V such that it won't be 0. It won't be 0. It's called an eigenvector of a hat. If what happens, if the following happens, if a hat times B is just lambda times B for some lambda in K. Böyle bir vektör varsa buna eigenvektör, burada eigenvalue diyoruz. Bu lambda sayısına da eigenvalue diyoruz. The scalar lambda is called the corresponding eigenvalue. So, eigenvalues and eigenvectors comes in pairs. This is an eigenvector. This is the corresponding eigenvalue. So that A times this vector is lambda times this. Okay. In our case, these are the eigenvalues, and now I'm looking for eigenvectors. So let's start with this one. I want an eigenvector V1 so that A times V1 should be lambda 1 times V1. As I have done over there, As I have done over there. Okay, so these are the eigenvalues. I am looking for an eigenvector, and this is the definition of eigenvalue and eigenvector. This gives me what? This gives me the following: A minus lambda 1 times identity V1 is 0. And by definition, eigenvector is not 0. The V1 is not 0. That implies yeah, buna gerek yok. Pardon. Bunu yaptık zaten. Okay. I have this. All right. So V1 should satisfy that equation. Now let's see that equation. So A minus lambda 1 times identity. A minus lambda 1 times identity. What is this? 0, 1, 1, 1 minus lambda 1, 0, 0, lambda 1. So what is this? Times lambda 1, 0, 1, 1 minus lambda 1. And what is the equation I need to solve? I need to solve the following equation. A minus lambda 1. A minus lambda 1 times identity, which is just minus lambda 1, 0, 1, 1 minus lambda 1, times V1. Efendim?
Minus lambda 1 and 1.
Oh, yeah, here is 1. No, this is 0, but this is 1. Şurada ama şey yok. Bir dakika ya. Ha, tamam, doğru. Şunu güzel. Tamam. Tamam. V1 vektörünün, suppose the entries of V1 are just A and B. Okay. A and B. So this is 0, 0. Well, this gives me two equations, right? I cannot just multiply both sides with the inverse of this matrix because by construction, this matrix has no inverse, right? So you have to just solve this system. The only other way we know, we just by hand try to solve it. So minus lambda 1, I write equations. Minus lambda 1 times A plus B equals 0. And then A, and then 1 minus lambda 1, B equals 0. I have two equations and two unknowns, but actually these equations are the same. Where is that? You see, if you multiply this one by lambda 1 times 1, and this one by 1, and add them up, you get what? You get the following. Bu denklemi bununla çarpıyorum, bunu da 1 ile çarpıp topluyorum ki şu B'nin katsayısından. To get rid of the variable B, I just multiply this one with this constant, this one with 1, and then add them up. So we get minus lambda 1 times lambda 1 times lambda 1 minus 1 times A plus, okay, lambda 1 minus 1 plus 1 minus lambda 1 times B equals 0. Now, this is already 0. Yani, bir tane daha A var. Yani, plus 1 A. Değil mi? Bunu söylediniz değil mi? Okay. What is this? Well, this is just minus lambda 1 squared minus lambda 1 minus 1 times A. Okay. Equals 0. Bu zaten 0. Ama bu da 0. Değil mi? Lambda 1 is a root of this polynomial. Nerede o? Okay. So this is also 0. So you get what? 0 is 0. Well, like this, we don't get a contradiction, but this is useless. This means what? This means the following. These two equations are the same. If you multiply this with this constant, you just get the same equation. Just multiply with -1. So it means that, you know, this two tells us the same. Bu bir şey söylüyor, bu da aynı şey söylüyor. But we understand anything if it is said just only once, so we don't need this, right? Well, there, because it is useless. Okay. Yani bize 2 kere söylenmesine gerek yok, değil mi? Bir kere de anlıyoruz. O yüzden birini atabiliriz. Okay, now to close out what we get. So let's just concentrate on the first one. How can we solve this? Well, this has infinite many solutions actually. I am trying to find A and B, right? I can give any value to B and obtain A. I don't want the 0 vector, so I should keep away from 0. So let's just A equals 1. Then what is B? B is just lambda 1 times A, right? B is just lambda 1 times A, and A is 1, so this is just lambda 1. So my vector, I can take my vector B1 as follows: A, B. The first one is just 1. The second one is lambda 1, the golden ratio, right? Lambda 1. What if I choose 2 here? Well, if you choose 2 here, then you just get 2 lambda 2, 2 lambda 1, right? Because B will be just 2 times lambda 1. So you get 2 times this vector. If you put 3 here, you will get 3 times this vector. So you just get multiples of the same vector. All I need is just one eigenvector, and I have already found one of them, so I can stop here. So this is an eigenvector, and you can check that. A times B1 is really lambda 1 times B1. Okay. İsterseniz yapalım bir tanesini. 0, 1, 1, 1, D1. D1 is what? It is 1 plus lambda 1. So if you multiply with this, you get lambda 1 and then 1 plus lambda 1. Okay, now what is 1 plus lambda 1? 1 plus lambda 1. 1 plus lambda 1 is just lambda 1 squared. Right? Lambda 1 squared minus lambda 1 minus 1 is equal to 0. Therefore, lambda 1 squared is just 1 plus lambda 1. So instead of this, I can just write lambda 1 squared. And this is just lambda 1 times 1 lambda 1. So lambda 1 times d1. So A times d1, this is my d1, is just lambda 1 times d1. Come on. Okay. Evet, silebilirim. Zaten başka yer kalmadı. Okay. What about the second eigenvector? What about number 2 and we're going to give 1 minus root 5 over 2 and v2. You can repeat what we have done. For number 1, the vector was 1, number 2. Similarly, you see that v2 is just 1, number 2. Yani şöyle lambda bir neydi? 1 artı 5 bölü 2. V'li neydi? Şuydu. 1 artı 5 bölü 2 değil mi? V2 nedir? Pardon, lambda 2. Lambda 2 is just 1 minus root 5 over 2. And these two is just the same. 1 minus root 5 over 2. You see a pattern here, right? What's that pattern? These two numbers are their conjugates, right? You learn in high school conjugate numbers. They are conjugates. And you see these are also conjugates. So if you find one of them, the other one will be conjugate. If the eigenvalues are conjugates, okay, check. Let's another story. It is related to so-called value theory, actually, but we don't talk about this. Come on. Eigenvalues, so we found eigenvectors. We will continue in the second hour. Let me stop here.